Hi, I am Dr. Harikrishna Mulam, Associate Professor, Department of EIE, VNR VIGNANA JYOTHI. In this lecture, let us see one more problem related to time response analysis. Play the video at 1.5x speed or 2x speed to save some time. A positional control system is given with velocity feedback as shown in figure. So this is the block diagram of the positional control system, and it has a open loop transfer function of 16 by s into 0.8, whereas feedback transfer function h of s is this. What is that we need to find for such system? You need to find the response of the system. That means you need to find C of t, response of the system, when the input is unit step input, that is R of t is equal to unit step input, which is mathematically written as 1. And they also mentioned that the zeta damping factor of this system is 0.5. And it is also asked to find rise time, peak time, maximum overshoot, and settling time. That means we need to find all the time domain specifications of the system. Okay. And G of S, let me write G of S, open loop transfer function of this positional control system is 16 by S into S plus 0.8, which is S square plus 0.8S. And H of S is equal to Ks plus 1. Whatever may be the problem, generally first you need to find the closed loop transfer function of the system. Therefore, let us find closed loop transfer function of this system. It is given as G of S by 1 plus G of S H of S. Therefore, closed loop transfer function is G of S, that is 16 by S square plus 0.8S whole divided by 1 plus G of S is 16 by S square plus 0.8S into H of S is Ks plus 1. If you simplify this, the numerator will be 16 and denominator will be S square plus 0.8S plus 16Ks plus 16. That is equal to 16 by S square plus 0.8S plus 16Ks. If you take S out, it will be 0.8 plus 16K times of S plus 16. So this is the transfer function of the system, of course, in terms of K. Always compare the transfer function of the system with the standard way of representing the second order transfer function so that you can get the value for zeta, omega n and k values. Therefore, compare it with the omega n square by s square plus 2 zeta omega ns plus omega n square. If you compare them, you will get omega n square is equal to 16. That is omega n is equal to square root of 16, which is equal to 4 radians per second. Then if you compare this term, yes, coefficient of S with coefficient of S here, 0.8 plus 16K is equal to 2 zeta omega n. And it is said that zeta value is 0.5 for the system. Therefore, 2 into zeta is 0.5 and omega n is 4 radians per second. Therefore, 0.8 plus 16K is equal to this, which is equal to 2 into 0.5 is 1, 1 into 4 is 4. Therefore, 16k is equal to 4 minus 0.8, which is equal to 3.2. Therefore, k is equal to 3.2 by 16, which is equal to 0.2. So, for the damping factor to be 0.5, the k value should be 0.2 in this system. And therefore, finally, let me find the final expression for closed loop transfer function, which is equal to 16 by s square plus 0.8 plus 16 into k, that is 0.2 times s plus 16, that is equal to 16 by s square plus this is 3.2 plus 0.8, which is 4s plus 16. This is the closed loop transfer function of this positional control system, and its undamped natural frequency is 4 radians per second. As the damping factor is 0.5, such a system is underdamped second order system. Underdamped second order system. Okay, then once we have found this, if at all the marks allotted for this question are comparatively less, you can directly use the formula to find the response of the system. Therefore, response of the system C of t is equal to 1 minus e power minus zeta omega n t by square root of 1 minus zeta square into sine omega dt plus theta. We have already found several times how to find the damped frequency of the system, omega d, and theta of the system. So omega d is omega n square root of 1 minus zeta square. Omega n is equal to 4. Square root of 1 minus zeta is 0.5. So 0.5 whole square. And if you find this value, it will be around 3.464 radians per second. Similarly, if you find theta, theta will be equal to tan inverse square root of 1 minus zeta square by zeta. Therefore, tan inverse square root of 1 minus zeta is 0.5 whole square by zeta is 0.5. If you find its value, okay, in degrees it will come around 60 degrees, but we need theta value in radians. Therefore, if you multiply it by pi by 180 degrees, it comes around 1.047 radians. 047 radians. Therefore, a response of the system is equal to 1 minus e power minus zeta value is 0.5, omega n value is 4, t by square root of 1 minus zeta value is 0.5 whole square into sine omega d value is 3.464 radians per second into t plus theta is 1.047 radians. Therefore, it is equal to 1 minus e power minus 2t divided by square root of 1 minus 0.25 into sine 3.464 t plus 1.047. That is equal to 1 minus this 1 by square root of 1 minus 0.25 will become 1.154 into e power minus 2t sine 3.464t plus 1.047. This is the response of the given positional control system when the input is a unit step input. Okay. Then we can find all the time domain specifications of the system if you know zeta and omega n value. Zeta value is 0.5, omega n value is equal to 4 radians per second. If you know these two values, you can find all the time domain specification. Let us first find rise time. Rise time is given as pi minus theta by omega t. Pi value is 3.142 minus theta value is 1.047 divided by omega d value is 3.464. And if you calculate its value, it comes around 0.6046 seconds. So the time taken by the response to reach 100% of the final value for the first time is called as rise time, and in this system that rise time is 0.6046 seconds. Similarly, if you find peak time by the formula pi by omega d, which is equal to pi is 3.142, omega d value is 3.464, the peak time will come out as 0.907 seconds. This is the time taken by the response to reach the first peak value for the very first time. Okay. Next, settling time. Settling time is given by 4 by zeta omega n. If the steady state error is considered to be 2%, and this is given as 3 by zeta omega n if at all the steady state error is considered to be 5%. Therefore, 4 by zeta is 0.5 and omega n is 4, which comes around 2 seconds. Where 2 seconds is the settling time if you consider steady state error as 2%. If you consider steady state error as 5%, this will be 3 by 0.5 into 4. It is around 1.5 seconds. 1.5 seconds. And the last one is percentage overshoot, that is percentage MP, which is given as e power minus pi zeta by square root of 1 minus zeta square into 100. Therefore, e power minus pi zeta value is 0.5 divided by square root of 1 minus zeta square is 0.25 into 100. If you find its value, it comes around 16.3%. So like this, you can find the response of the system directly by using the formula for the response of second order underdamped system when the input is unit step, and you can find all the time domain specifications if comparatively the marks allotted to the question are less. But if it is given for a long answer question, then maybe you need to find this response of the system from the transfer function of the system using partial fractions and inverse Laplace transform without directly using this formula. In such a case, let us solve that part also. We understood that the transfer function, closed loop transfer function of this system, that is equal to ratio of Laplace transform of output to the Laplace transform of input, is given as 16 by s square plus 4s plus 16. Therefore, C of s is equal to 16 by s square plus 4s plus 16 into r of s. That is equal to 16 by s square plus 4s plus 16 into, we know that input r of t is equal to unit step input. Therefore, Laplace transform of it is equal to 1 by s. So here it is 1 by s. But we already told as zeta value is equal to 0.5, the system is underdamped. underdamped system, and the poles of the system or the roots of the characteristic equation of this transfer function will be complex conjugate pair. Complex conjugate pair. Therefore, as there is no direct inverse Laplace transform formula for this C of S expression, to get finally the expression for response of the system, first of all, you need to get the partial fractions for this expression. Therefore, partial fractions, because of this complex conjugate pair of poles, okay, the partial fractions for this expression is written as A by S plus BS plus C divided by S square plus 4S plus 16. Okay. So the residues A, B, C should be found. A can be directly found using the formula C of S into S when S is equal to 0. That is equal to C of S is 16 by S square plus 4S plus 16 into 1 by S. This is entire thing is C of S into S when S is equal to 0. This S gets cancelled. When S is equal to 0, this becomes 0, this becomes 0. 16 by 16 is equal to 1. Therefore, C of S that is 16 by S square plus 4S plus 16 into 1 by S is equal to A by S. A is 1 by S plus BS plus C divided by S square plus 4S plus 16. The residues B and C are found by taking the LCM on the right hand side. Okay. So, and comparing the numerator terms on both left hand side and right hand side. So, the expression on the right hand side is S square plus 4S plus 16 into S, and the numerator of this is S square plus 4S plus 16 plus BS plus C into S, that is BS square plus CS. The expression on the left hand side is 16 by S square plus 4S plus 16 into S. Now, if you compare the coefficient of S square on the left hand side numerator with the coefficient of S square on the right hand side numerator, it will be, what is the coefficient of S square on the left hand side? It is equal to 0. That 0 is equal to coefficient of S square in the right hand side is, this is 1 plus B. Therefore, 1 plus B. Therefore, B is equal to minus 1. Similarly, if you compare the coefficient of S on the left hand side numerator with coefficient of S on the right hand side, it will be, on the left hand side coefficient of S is 0. On the right hand side it is 4 plus C. 4 plus C. Therefore, C is equal to minus 4. Like that, you need to find the residues A, B, C in order to get the final partial fraction for the expression. Therefore, C of S is equal to 1 by S. Here B has minus sign, C has minus sign, I am taking out. Therefore, here it will be minus. Therefore, BS plus C. So, as I have taken negative sign out already, BS will be simply S plus 4 whole divided by S square plus 4S plus 16. Again, as there is no direct inverse Laplace transform formula for this, maybe you need to adjust it so that you will be able to use inverse transform formulas like S plus A by S plus A whole square plus omega square, and which is given as e power minus at cos omega t. Similarly, you can use the formulas like inverse Laplace transform of omega by S plus A whole square plus omega square, which is given as e power minus at sine omega t. In order to use such formulas, you need to rearrange this expression. You need to rearrange this expression. Let us see further. So, C of s is equal to 1 by s minus s plus 4 by s square plus 4s plus 16. It can be written as s square plus this 4s can be written as 2 into 2s. Therefore, this 2 is like a. Therefore, in order to get the expression of s plus a whole square, you need to split this 16 accordingly. Therefore, 1 by s minus, let me first write the denominator term, s square plus 2 into s, as a is 2, 2 square is 4, and if 4 is subtracted from 16, the remaining is 12. Therefore, this s square plus 2as plus 4 can be written as s plus 2 whole square. Therefore, even this numerator I am writing it as s plus 2 plus 2. Therefore, 1 by s minus, I would like to separate up to here, that is s plus 2 by s square plus 2 into 2 times s plus 4 can be written as s plus 2 whole square plus 12 can be written as square root of 12 whole square minus, what else is left over? This 2 is left over. 2 by s plus 2 whole square plus square root of 12 whole square. This is in the standard form, but this is not in the standard form. Therefore, in order to make it in the standard form, you need to multiply it with the square root of 12 as well as divide with the square root of 12. Therefore, C of s will be equal to 1 by s minus s plus 2 by s plus 2 whole square plus square root of 12 whole square minus this 2 by square root of 12 is taken out, 2 by square root of 12 into square root of 12 by s plus 2 whole square plus square root of 12 whole square. Therefore, if you take the inverse Laplace transform of this, C of t is equal to inverse Laplace transform of 1 by s is equal to 1. Therefore, 1 minus, we have already shown the inverse Laplace transform for this, that is s plus a by s plus a whole square plus omega square. Its inverse Laplace transform is e power minus at cos omega t, and for this it is e power minus at sin omega t. So based upon that expression, you can write e power minus 2t cos square root of 12. Okay, and this root 12 can be written as square root of 4 into 3, that is which can be in turn written as square root of 4 is 2 into square root of 3. The 2 gets cancelled, therefore left over is minus 1 by root 3, and the inverse Laplace transform of this is e power minus 2t sine square root of 12. That is equal to 1 minus, if you take this minus e power minus 2t common, minus e power minus 2t common, what else is there? Cos square root of 12t plus 1 by square root of 3 sine square root of 12. Okay. But, so though this can be called as the response of this positional control system, I wanted to finally express in the form of a standard way of representing the response. Therefore, C of t is equal to 1 minus e power minus 2t, and if you take the LCM of these two, the denominator will be square root of 3 cos root 12t plus sin root 12t. Okay. Then before proceeding further, let us take this right angle triangle with angle theta here. Opposite side is square root of 1 minus zeta square. Adjacent side is zeta. So zeta, we know its value is 0.5. Okay. I would like to write it as 1 by 2 here. And this opposite side is square root of 1 minus zeta is 1 by 2. Zeta square is 1 by 4. Therefore, this will be, if you find it, square root of 3 by 2 will be the opposite side. And hypotenuse is always 1. And based upon this triangle, we can write sin theta is equal to root 3 by 2, whereas cos theta is equal to 1 by 2. We can use these values so that this expression is represented in the form of sin A plus B form. Therefore, C of t is equal to 1 minus e power minus 2t by root 3 into, okay, I would like to multiply this cos root 12t with the sine term, that is root 3 by 2. As we cannot do like that, you need to multiply it with 2 by root 3 also into cos square root of 12t plus, as this is sine term, I would like to multiply it with cos term, and cos theta is equal to 1 by 2. Therefore, 1 by 2 into, as we cannot divide it by 2, multiply it also with the 2 and sine root 12t. Okay. That is equal to C of t is equal to 1 minus e power minus 2t by root 3. So the response of the system that we got is 1 minus e power minus 2t into cos root 12t plus 1 by root 3 into sine root 12t. So before proceeding further, let us consider this right angle triangle with an angle theta. We know that opposite side is square root of 1 minus zeta square, adjacent side is zeta, and in this problem zeta is 0.5. I would like to write it as 1 by 2. And if zeta is 1 by 2, you will get square root of 1 minus zeta square as root 3 by 2. And anyway, hypotenuse is always 1. And based upon these values, you can get sin theta is equal to opposite side by hypotenuse, that is root 3 by 2. Whereas cos theta is equal to adjacent side 1 by 2 by 1, which is 1 by 2. Okay, let us use these values in this expression so that the theta term is there in the response of the second order system. Therefore, C of t is equal to 1 minus e power minus 2t. So we need to rearrange this expression so that it looks in the standard way of representing the response of second order underdamped system. So we have cos root 12t and it should get sine term. Therefore, sine theta value I am writing root 3 by 2. But as you cannot multiply like that, I am also multiplying it by 2 by root 3. Therefore, overall its effect will become 1 plus 1 by 3 into sine root 12t. As sine term is there, I wanted to multiply with the cos term, cos theta term, and its value is 1 by 2. As I cannot multiply it just with 1 by 2, I am also multiplying it with 2 as well. Therefore, overall its multiplication will become unity. Okay. So, now this is equal to 1 minus e power minus 2t into cos root 12t into square root of 3 by 2 is written as sine theta into 2 by root 3 plus sine root 12t is there. As sine term is there, we have multiplied with the cos term, that is 1 by 2. So this 1 by 2 is cos theta. What else is left over? This are over. So 2 by, this is root 3, boss. This is root. So 2 by root 3 is there. Therefore 2 by root 3, 2 by root 3, if you take it out, 1 minus e power minus 2t into 2 by root 3 into let me write this first, sine square root of 12t cos theta plus cos square root of 12t sine theta. That is equal to 1 minus this 2 by root 3, its value comes around 1.154 into e power minus 2t, and this is like sine a cos b plus cos a sine b. Therefore, you can write it as sine of square root of 12t plus theta. That is equal to 1 minus 1.154 into e power minus 2t sine of square root of 12 is equal to 3.464 into t plus theta we have already found before, that is theta here. If you see, theta value is 1.047 radians. Therefore, theta value is equal to 1.047 radians. So this is the response of this positional control system when the input is a unit step. Now this expression is looking similar to that of standard way of representing the response of second order underdamped system. That is why this expression is rearranged in this form. Otherwise also, if you do up to here, this is also right. So based upon the number of marks allotted to the question, you need to follow appropriate procedure. If the number of marks are less, you can directly use the formula for response of second order underdamped system. If the marks allotted to the question are more, you need to go with the partial fractions and taking the inverse Laplace transform to find the final expression for response of the system. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.